those of us over a certain age, one dramatic change we've all experienced in our lifetimes is the move toward a safer society. In the past, virtually everyone would take part in risky activities, such as driving in a car without a seatbelt or riding a bike without a helmet, as the rule rather than the exception. In recent years, people have become more educated regarding the avoidance of unnecessary risks, and gradually, attitudes have changed for the benefit of us all. This newfound awareness is appearing worldwide, whether it be building codes for new properties or protection enhancements in transportation vehicles. Evidence can be found in many aspects of our everyday lives that proves how the hard work and diligence of the world's brightest engineers and planners have made all of our lives safer and more enjoyable. The advance toward a safety-first mentality has been embraced by both the private sector and by government, with one of the most high-profile shifts coming from the government agency, NASA. Although NASA has always been focused on safety, recent developments in technology, as well as a desire to perfect systems and policies, has led to a heightened awareness within the space agency. Perhaps the most significant organization within NASA that typifies this culture is the aptly named NESC, or NASA Engineering and Safety Center. This highly skilled group is pushing the boundaries on safety even further in an effort to make systems within the agency as safe as possible. Today on NASA X, we will follow members of the NESC as they test new designs to gain as much knowledge as possible about engineering safety. We will focus specifically on several new designs that will affect future spacecraft. And we will see how computerized modeling paired with hardware tests are now being used to pave the way for safe space systems of the future. As is so often true, our greatest lessons come from our greatest failures. What we learn from these failures influences our future decisions. This was indeed the case for NASA after the 2003 Columbia tragedy. Not long after this accident, NASA's Engineering and Safety Center was formed in an effort to find new ways to adequately address the importance of safety. NASA realized the necessity to perform value-added independent testing, analysis, and assessments of high-risk projects to ensure safety and mission success. This type of approach assists in proactively identifying issues beforehand, helping NASA avoid future problems. At the core of the NESC is a group of technical specialists pulled from all NASA centers and from a group of partner organizations external to the agency. This highly trained group works tirelessly to identify and address potential concerns before they become major problems. Their technical prowess has been used in everything from creating composite crew spacecraft designs for NASA to being asked to help with a Chilean mine disaster a few years ago. With each challenge given to them, the team strives to increase safety and mission assuredness to a highest possible standard. The NESC is currently working on myriad technologies within NASA, but one area that has moved to the forefront in recent years is in the development of space-rated equipment for future crewed missions. Crewed missions into space are obviously very risky. Even though NASA has years of experience in missions with crews on board, new designs and materials are continually being implemented, which in turn require additional testing to mitigate any safety concerns. One area where additional testing was requested came recently from NASA's Commercial Crew Program. They needed help evaluating something called Frangible Joints for human spaceflight. These are joints that are located at the separation point of each rocket stage that help each stage release from one another, and if they do not work correctly, then a mission failure is almost assured. To better understand what this is, let's examine how a spacecraft works. Generally, when you see a rocket on a launch pad, like the Saturn V, or a rocket launching satellites, for example, you are not just looking at one big rocket, but a series of smaller vehicles attached to one another. This is called a multi-stage rocket. In this type of staging, the first stage is at the bottom and is usually the largest. The second stage and subsequent upper stages are above it, usually decreasing in size. In the typical case, the first stage fires to propel the entire rocket upwards. When that stage runs out of fuel, it detaches from the rest of the rocket and falls away. This leaves a smaller, lighter rocket which then fires the next stage. This process is repeated until the final stage's motor burns to completion. If these stages don't separate from one another, then the rocket will not be able to break free of the atmosphere and will fall back down to Earth. If an event like this were to occur with humans on board, the crew's lives would be in peril. This is why the NESC is so interested in this process. Frangible joints have been used on rockets for many years, but most crewed missions of the past relied heavily on other stage separation devices, including frangible nuts and bolts. Although effective, frangible nuts and bolts send out debris that could be damaging to the craft, and they also cause excessive vibration that could damage hardware aboard the vehicle. In contrast, frangible joints do not send out shrapnel and do not cause the same level of vibration, making them a likely contender to be used on future missions. Although there is already years of data on frangible joint use, the NESC team has determined that more detailed understanding of these joints must occur before they can sign off on its use for future crewed missions. Here is the frangible joint principal investigator, Clinton Craig, to explain.
Frangible joints have been used for quite some time in the United States, within NASA, within the U.S. military. But it's only recently that they've been suggested to be used with human-rated vehicles. So this is a frangible joint that's been functioned. It was used on the MLAS, the Max Launch Abort System project that the NESC accomplished a few years ago. But this is part of that was used. In this particular design, which is an Ensign Bickford Tang and Clevis design, there was a part that attached here at the top, and within this was the stainless steel tube. It's more round now, but in the beginning it was oval and fit neatly in between the space here between the Clevis and the Tang and the Clevis. And within the stainless steel tube is a charge holder, which is kind of like a squishy eraser kind of substance, and there's a hole in that charge holder where the mild detonating fuse, the MDF, gets inserted. And so when you want this to function, the idea is you detonate both sides of the MDF and causes the stainless steel tube to expand. And when it expands, these pre-machined notches on either side of the clevis break, and that's all there is. So it's a pretty simple design, but one of the things that we've been asked to do is to fully characterize this design, to find out if there are any sensitivities in the design, or if the spacecraft encounters abnormal conditions, is it still going to function, those kind of things. Part of the problem is with the frangible joints is they are zero fault tolerant, and that means that a single fault in the explosive charge within a frangible joint, if there is a single fault, then it's going to fail. And there are some regulations within NASA that say you have to have a single fault tolerant system, which means one single fault won't prevent proper operation of whatever it is. So that's why we've gotten into the frangible joint business. After our written report of the historical background and things like that, we were asked to actually carry out this test program, and that's currently what we're in the process of doing.
It affects essentially all NASA missions. Anytime you've got a stage separation, you've got to have some kind of mechanism to accommodate that. There's other ways to do that other than frangible joints. You can have frangible nuts, you can have pyrotechnical and pneumatically operated bullpens, things like that. But they've got to have the same level of reliability. And one of the simplest, most straightforward ways to do that, and ways that will create the minimum amount of fragmentation, is frangible joints. So you name the program, whether it's a commercial crew program, it's the new SLS program coming up, it'll use frangible joints. Every mission we plan, Moon, Mars, beyond, will have to deal with stage separation.
Frangible joints have evolved over the last 2 or 3 decades, and they weren't around when the shuttle, to my knowledge anyway, the shuttle was developed. But they have some attributes that people really like about them. In the old days, sometimes they used the shape charge, for example, to separate different portions of the vehicle as it's going up, the first from the second stage. But the shape charges created a lot of shock and debris sometimes, and so that was a downside of using that. The frangible joints themselves, since the explosive is contained within a stainless steel tube, there's no debris, essentially. The only thing that happens is the frangible joint breaks and the spacecraft goes on its way.
Much of the testing for frangible joints is being done here at the White Sands Test Facility in New Mexico. Located close to the famous White Sands National Park, this facility's infrastructure and isolation make it an ideal place to test materials like this. We caught up with the team as they were going over some recent findings and preparing for an upcoming test.
Team members from 7 NASA centers, which I think is, it's pretty good. And we have a number of technical experts from industry, but we've got about 20 or so core members of the team that are contributing.
Each team member brings a breadth of knowledge and experience to the table to help round out the core group of decision makers. Located in this nondescript building, researchers have been testing different frangible joint pieces. As is the norm in research-based testing like this, test planners are performing incremental tests to create a baseline to better understand the characteristics of the joint. Here is test engineer Dox Rios, who will walk us through the test for today.
So the test that we have currently set up in here is it's our what we're calling a confidence instrumentation and checkout testing. Prior to getting the higher fidelity, more expensive test hardware which we'll be using. So we've fabricated in our machine shop sample little short joints that are 2-piece design. So you have a clevis piece and then you have a tang piece, and then in between the two you have a stainless steel tube that is loaded with HNS pyrotechnic. And once you let it go, the tube expands, forcing the clevis legs to open up at little, what we call a separation plane, and then the two come apart.
Here at White Sands, they have made several hundred lower fidelity joints to test in this chamber. Each piece is different and tests different aspects of the joint. Some pieces have more explosive than others, some are curved, while others are flat. Some are thicker than others, but each one helps to fill in the gaps of our knowledge to help us understand what will be the best design. As researchers gain more knowledge, they will begin to test the more expensive, higher fidelity pieces, which are nearly identical to the actual pieces that will fly on board missions. On this day, they will be testing a lower fidelity piece that is part of the baseline study. In this special room, the test article is placed on the stand. It then has different strain gauges, lasers, and other instruments attached or pointed in its direction to help measure what happens after the detonation takes place. Each instrument is important, but some of the most useful tools in the room are the various high-speed cameras that will capture the separation of the joint. Each camera is trained on a specific section and will show different angles, capturing the tests at millions of frames per second, allowing a detailed look at the separation. As the data starts to pour in, the NESC team begins to get a look at what the high-speed cameras and lasers captured.
All right, so we just finished running one of the tests, and it looks like we did get good separation. Right now, everybody's going through and reviewing their data to verify that they actually did record. Again, that's part of the validation of the data to see if what we get out of it. Right now, is just verifying that we did get data, and they're going to go and look at it to try to validate it. What I mean by the joint actually did separate, which is the intent of the joint, is supposed to separate. So whether each one actually looked and they actually saw the crack initiate, to try to do what we were trying to do, that's what we still need to go back and look at.
Preliminary results seem to suggest a successful test. Now researchers will go back and place the data into a computer model to show the complicated dynamics around that particular separation. Tests like this test will go on for about a year or so, until the planners are sure they understand all the dynamics involved with frangible joint separation. If frangible joints get through this testing phase with flying colors, then we may all soon be seeing them on spacecraft in the near future. Far from just focusing on one issue, the NESC is also looking at other safety issues related to human spaceflight. One area that has garnered much interest recently is in the area of shell buckling. If you have ever seen old footage of early rockets collapsing on themselves or breaking apart on the launch pad or just after takeoff, then you know what shell buckling looks like. Because so many launch vehicles are cylindrical, this type of buckling is one of the primary failure modes that occur in launch vehicle structures. In the past, the way researchers would get around the structural problem would be to make the launch vehicle much stiffer, which in turn made the craft much heavier. But with an average cost of about $10,000 per pound to launch something into space, each extra pound drives up costs of missions and also limits the size and amount of scientific instrumentation that can be flown. As you may well imagine, NASA researchers are not satisfied with the status quo and have begun to design new shells that are structurally very strong, but also much lighter as well. Here is NASA's Mark Hilberger to explain.
Designing a launch vehicle, one of the primary failure modes is buckling. Buckling is basically a loss of stiffness in your structure when the sides of the structure collapse, like a beverage can. And in the early years, they were using very conservative design guidelines and factors associated with that design problem. And one of our main goals was to provide new factors that are less conservative and provide these factors to the designers of our more modern launch vehicles, with the main goal of providing design guidelines that would enable lower weight structures, but structures that are actually more robust and safer because we're taking into account modern design features, modern materials, and construction methods. The past design guidelines for shell buckling were produced based on data from the 1930s to the 1960s, when they were just then trying to understand the buckling phenomenon. And if you've ever crushed a beverage can under your foot, it's a very dynamic, complex collapse type of behavior. So they were very conservative about how they developed their design guidelines. Since then, we've become a lot smarter in the physics of buckling. We have very accurate computer simulations that are backed up by very carefully conducted testing. And so what our project has been doing has been carefully studying the buckling problem for modern day launch vehicles and developing very accurate simulations of the buckling process. When you have a launch vehicle, they're subjected to many different types of loads, and the primary loads that we're worried about are the ones involving compression of the structure or bending. When the launch vehicle's flying through the atmosphere, it sees aerodynamic loads that cause bending as well as compression loads, and those loads can actually cause the structure to buckle. And while these are much, much larger structures, they still exhibit the same type of buckling failure modes. And it turns out to be one of the primary driving design factors in these vehicles. So it's very important that we provide safe design guidelines, but at the same time provide guidelines that enable efficient structural design. So we're very much interested in having a very lightweight structure. We've conducted 4 tests on these smaller scale, 8-foot diameter barrels. These are about 30% scale to the full-scale SLS type vehicle. We've also completed 2 full-scale tests, one most recently in December of 2013. And we're running these tests to validate our computer simulations. Because in the past, they relied solely on test data to provide guidelines for design. What we're doing now is we're validating our computer simulations with a select number of tests and then using the analysis tool to develop the design guidelines. So that saves us a lot of time. It also saves us a tremendous amount of money in testing because these tests are very, very expensive. One of the highlights of the project so far is we've actually been able to develop and implement a new set of factors for the NASA's Space Launch System, the SLS vehicle. And they've implemented them into their core stage design. Their core stage is their first stage of the new rocket. And they've seen significant mass savings as well as some time and cost savings associated with the new factors. I think this is definitely going to stand the test of time because not only is it just going to be a set of numbers for the types of structures we're building now, but it's actually a methodology that's being defined, so it can be applied to whatever future constructions or whatever future materials come around. There's a lot of work that will be associated with that, but we've at least shown a path forward on how you can design, test, and analyze these types of structures at a very high level of fidelity.
The NESC is looking at many ways to make NASA safer, and as is the norm with NASA, often this safety that is highlighted for NASA trickles down into products that can be used by the general public as well. In coming years, NASA explorers will once again be pushing back the boundaries of the unknown as they travel into near-Earth orbit and beyond. And it is comforting to know that there is a dedicated group within NASA who are working hard every day to make those future missions as safe as possible.